We already learned how to solve systems in two different ways. We did it by substitution, we did it by graphing. So here's the third way that we're going to solve systems, and that is by elimination. Sometimes we also call this linear combination. This is another way of talking about solving systems in this method. So what if you were asked to solve this problem that's in front of us by substitution? In the previous cases when we did substitution, there was always a nice, easy variable to solve for. In this case, this looks a little messy. What would you solve for? For x, for y? I don't know. Suppose we took this top one here. We tried solving it for x. We'd get 4x equals negative 5y plus 13. Then we would divide everything through by 4. And we would get x equals negative 5/4 y plus 13/4. Then we'd have to substitute that into here. So we multiply 7 by negative 5/4 and 7 by 13/4, and then find common denominators with the 3y. It looks like it's getting messy. It looks like I'd like another way to solve this. So I'm going to solve this system by what we call elimination. So let's start with a couple of easier ones before we get to the more challenging ones. The idea is, like the word says, we're going to eliminate one of the variables by adding the two equations together. Now this first one, you notice this is the same one that we started with when we did it by graphing. We did it by substitution. Now let's do it by elimination. This one is already set up for us. And how do I know? Because look at the y's. If I add a y and a negative y minus y goes to 0. So let's add these two lines together. X plus x is 2x. The y's go away, right? Positive y, negative y, 0 out. On the other side, 4 plus 2 is 6. Divide everything through by 2. Our goal is to get down to one variable, get an answer for one variable, put it back into the other. Okay, so if x is 3, then put it back into the first line. 3 plus y equals 4, so y must be 1. And not surprisingly, we got the same answer that we did solving that same system the first two times. All right, look at the second one. Now, the reality is you can choose to get rid of x or you can choose to get rid of y. I'm going to do the one that takes the least amount of work. So if you look at the x's, if I were to try to get rid of these x's, between a 5 and a 3, I would need to get a 15x and a negative 15x. So I'd have to multiply the top row by 3 and the bottom row by negative 5. Not the worst thing in the world, but if I try to get rid of the y's instead, you realize I could do that by multiplying this bottom row by negative 2. Because then I'll get a negative 2y up on the top. Negative 2 times negative y is a positive 2y. And I'll be able to multiply just one row and get rid of the y's. Wise decision, you might say. So in this top row, I get a 5x minus 2y equals 8. Multiply everything on the bottom row by negative 2. So I get a negative 6x plus 2y equals negative 14. All right, so add the x's together. 5 plus negative 6 is negative 1, so I get a negative x. Look at this, the y's go away. Negative 2y, positive 2y go away. On the other side, 8 minus 14 is negative 6. So multiply through by negative 1, x is 6. All right, if x is 6, let's throw it, I don't know, into the bottom equation. 3x minus y is 7. So 3 times 6 minus y is 7. 3 times 6 is 18, so let's subtract an 18 from both sides. Don't lose that negative sign. I get positive y, or actually I get negative y, equals negative 11. So multiply both sides by negative 1, and I get y is 11. So it looks like my answer is x equals 6, y is 11. Try it in the first row. I get 30 minus 22. Yes, that's 8. On the bottom row, 18 minus 11 is 7. So there's my answer. You can always go back and put these into both equations. If they work in both equations, then that's the solution. So some people like to see the procedure written out. Here the procedure is written out. So first of all, you notice that my equations were already given to me where the x's were underneath each other, the y's were underneath each other, the constants were underneath each other. Every once in a while, you'll come across a problem that is not set up that way, and you'll have to line them up correctly. So just double check to make sure it's set up in the way we want it. X's, y's, constant. All right, pick a variable to eliminate. So one of them we got rid of the y's. Actually, in both of them we got rid of the y's. You can get rid of the x's. I'm sure we'll do enough problems that we'll find some we get rid of the x's as well. Right? You may have to multiply both rows by a constant. You might be able to get away with only multiplying one so that the variables will add up to 0. Add them up, solve for the remaining variable, and then go back and substitute. When you get done, write your answer as an ordered pair. All right, so this is on the PowerPoint if you want to have a step-by-step guide as to how we do these things. All right, we're not going to do every one on here, but let's take a look at number 4. All right. For number 4, we got a 9x and a 6x, we got a 4y and a 10y. So the last couple we got away with just multiplying one row, or in the first one, not multiplying any rows. Now it looks like we're going to actually have to multiply both rows by something. So equal amount of work, I think. You want to get rid of the x's or get rid of the y's? I don't know. Maybe this time I'll get rid of the x's. So if I got a 9x and a 6x, least common multiple of 9 and 6 is 18. So if I can get one row to become 18x and the other row to become negative 18x, then the x's will drop out. So what do I have to do in order to make that happen? Well, 9 times 2 is 18, right? So multiply the top row by 2. 6 times negative 3 is negative 18. So if I multiply the top row by 2, bottom row by negative 3, it looks like I'll get rid of my x's. So 2 times 9 is 18, so I get an 18x. Don't forget, now everything is multiplied by 2. 2 times 4 is 8, so plus 8y. 2 times negative 3 is negative 6. Down the bottom row, negative 3 times 6 is negative 18. Negative 3 times 10 is negative 30. Negative 3 times negative 13, positive 39. Now add these together. The x's go away. 8 minus 30 is negative 22. 39 minus 6 is 33. So now divide both sides by negative 22. And I get y equals, if I take an 11 out of top and bottom, negative 3/2. All right, now we can put that into either equation out. Now maybe I'll pick the top one because the numbers look a little bit smaller on the top. So if I put this into the top row, I get 9x plus 4 times y, which I already know is negative 3/2, equals negative 3. And so I get 9x. 4 times negative 3 is negative 12. Half of negative 12 is negative 6. When I add a 6 to both sides, I get 9x equals 3. Divide both sides by 9. X equals 1/3. So it's a funky looking answer. X equals 1/3. Y equals negative 3/2. But there it is. That's my answer to the problem. All right, let's pick another one. Maybe we'll work on number 6. I'm going to flip this over to a different screen because I have no more room to write over here. All right, so here it is written on the little whiteboard that I have. What do I use to get rid of the x's or the y's? This one, again, has no real easy answer. It's easier to do it this way than to try to do this one by substitution. That would be a little bit messy. But what do I want to get rid of, the x's or the y's? I don't know. Maybe I'll get rid of the x's only because one's positive and one's negative. It looks like I'm going to have to multiply by essentially the other term. So I'll multiply the top row by 7, right? 7 times 9 is 63. 9 times negative 7 is negative 63. All right, so distribute that 7. So 7 times 9 is 63, so I get 63x. 7 7s are 49. And 7 times negative 14. 4 times 7 is 28. Carry the 2, 98, and it's negative. Down here, I got a negative 63x. I get a positive 18y. And I get a negative 36. All right, so like we planned, the x's go away. Add these together, I get 67y. Over here, they're both negative, so I'm going to get a negative something. 8 plus 6 is 14, carry the 1. 9 plus 3 is 12, plus 1 is 13. Okay. Divide both sides by 67. 134 divided by 67 is 2. Well, negative 2 because there's a negative sign in there. All right, now let's take that and sub it back to find what x is. So I get 9x plus 7 times negative 2 equals negative 14. So 9x minus 14 is negative 14. Look, if I add a 14 to both sides, over here I get a 0, and over there I get a 0. So is that possible? Sure. X is 0. So x is 0, y is negative 2. And now you realize that if you go back to the original problem, 7 times negative 2 is negative 14. 2 times negative 2 is negative 4. Problem's done. Right, so that's what that looks like. What about these funky looking problems, fractions and decimals? If you have something with decimals like number 9, multiply everything by 10 to clear everything out. Right? Multiply it by 10, you'll end up with a negative x plus 6y equals 13, 8x plus 6y equals negative 50, and then just solve from there. Same thing with fractions. Multiply top row, bottom row to clean something out, and then solve from there. All right, let's take a look at the special cases. All right, here are 2 special cases, and we want to know how to solve them and then what they mean. So that first one there looks pretty simple. Right? If I add them together, 5x minus 5x is 0. Negative 3y plus 3y is 0, so I just get 0. 23 plus 7, though, is 30. And now I got a really weird answer. 0 equals 30. What am I going to do with 0 equals 30? Well, think of it this way. How many times does 0 ever equal 30? It doesn't. So what this means is that there's no solution. There's never a time when 0 and 30 will have the same value. If you were to graph these, they would end up being parallel lines. There would be 2 lines with a slope of, it turns out, 5/3, but they have different y-intercepts. So you'll keep going up 5 to the right 3, up 5 to the right 3, and those lines will never cross each other. So if you solve by elimination, or even if you solve by substitution, you get something that looks like that. That means that there's simply no solution. All right, look at this next one. Maybe I'll multiply the top row by negative 2, and I'll get negative 2x minus 2y equals negative 8. The bottom row is 2x plus 2y equals positive 8. Add them together. Again, the x's go away, the y's go away. But this time what's on the other side goes away too, right? 8 plus negative 8 gives me 0. So do I just draw a smiley face and I'm done? What does it mean if 0 equals 0? Well, how many times does 0 equal 0? That's always true. Right? So what that means is that there's infinitely many solutions. It does not mean that any real number will work, though, right? So don't put all real numbers, because, for example, 0, 0 doesn't work. 0 plus 0 is not equal to 4, right? If I put a 0 in for x and a 0 in for y, it doesn't work. 0 plus 0 is not 4. So while you have an infinite number of solutions that do work, not everything works, all right? So there's infinitely many solutions. What does it look like if I graphed it? They'd be the same line. Right? Try solving it. Each one would be the line. If I take this bottom one and I divide it by 2, I'm back to the top line. So if you graphed it, they would end up being the same line. All right, let's try a couple of application problems here. So we got a cruise boat. Travels 72 miles downstream in 4 hours, returns upstream in 6 hours. Find the rate of the stream. So in other words, if you're in the river and you're rowing your boat gently down the stream, if you're going downstream, then the river is pushing you. And so you're getting a little bit of extra speed as you're going downstream because the water is with you. As you're going upstream, that water is pushing against you, and so it's trying to slow you down. The same thing, by the way, happens in airplanes. If you're traveling with the wind, then the wind is actually pushing that big airplane a little bit. If you're traveling against the wind is pushing against the airplane, and so now the airplane has to work harder to push against that wind that's blowing towards it. So we know that it's 72 miles total. Right? Even though it takes more time to go down, to come back than go down, it's still 72 miles. So let's pick a couple of variables. Let's let x be the speed of the boat. And let's let y be the speed of the stream, or the rate of the stream. The other thing that might be helpful is somewhere in physics, maybe they taught you that distance equals rate times time. So that must mean if I divide both sides by time, I get this equation that says distance divided by time is the rate. So let's do this for going downstream, and let's do it for upstream. The rate of the boat plus the rate of the stream equals the rate at which they traveled. So the rate of the boat is x. The rate of the stream is y. They're going in the same direction. How long did it take them? It took them 72 miles, 4 hours to go 72 miles. Now, if they're going upstream, it goes the other way. Here's the speed of the boat, but the stream is pushing against it. So you got to subtract rather than add. Do that. How fast did they travel? 72 miles took them 6 hours. So you can think of it as rate, right? You can calculate the two rates separately and then just throw it into the equation like that. So 72 divided by 4 is 18. 72 divided by 6 is 12. So really what I have is the system x plus y equals 18. X minus y is 12. That's the hard part. Once I set it up, then, look, this is just set up for me to add together. X plus x is 2x. The y's go away. 18 plus 12 is 30. So x is 15. So the boat was moving 15 miles per hour, which must mean that the stream is moving 3 miles per hour. So the other thing is always check the question to make sure you're answering the question. So don't stop at 15, because 15 is not the rate of the stream. 15 is the speed of the boat. You want the rate of the stream, substitute it back in. On the way downstream, that stream is pushing you 3 miles an hour. On the way back, it's pushing against you 3 miles an hour. So even though the boat's trying to go 15 miles an hour, the stream is pushing back, and it's not moving as fast. All right, one more. So we got a basketball game. Tina scores 37 points in a basketball game without making any three-point shots. So she scored 24 times, making some free throws. Just in case you're not familiar with basketball, free throws are worth a point, and the two-pointers are called field goals. So field goals are worth 2 points. Free throws are worth 1 point. It says she scored 24 times. So 24 times the basketball left her hand and went through the hoop. So all of her free throws, I can't use F for free throws and F for field goals, so maybe I'll stick with X's and Y's. X's for the free throws, Y for the field goals. How many of each ones did she make? So if it says how many of each did she make, then those are the things that get the variables. The free throws get one variable, field goals get the other one. I need two equations. So how many times did she score? All the free throws that went in plus all the field goals that went in adds up to 24. So I'm only talking about the times that the basketball actually went through the hoop. She may have tried other attempts that she didn't make, but of the attempts that she made, 24 times that basket went through the hoop. The only difference is where she shot it from. So now let's talk about points. 1 point for each free throw, 2 points for each field goal, adds up to 37 points. Now we got a system of equations. Let's solve. Maybe I'll multiply the top row by -1. My goal to clear out the x's. So I get -x minus y equals -24. Remember, everything gets multiplied by -1. Down the bottom, I get an x plus 2y, 37. Add them together, the x's go away. 2y minus y is y. 37 minus 24 is 13. So she scored 13 field goals, right, or 13 two-point shots. And she must have scored then 11 free throws. I mean, she must have gotten fouled out a lot in that game. check and see if that works. 13 times 2 is 26. Add 26 plus 11, sure enough, it adds up to 37 points. So knowing how many times the ball went through the basket and how many points she got total, and eliminating the 3-point shots, which I did only because we only have 2 variables. If we had 3 variables, we could have done a system where she has some 3-point shots as well. All right, so that's the end of this section. In the next section, we'll talk about inequalities and systems of inequalities.